Welcome back. In the last video, we went briefly through the CNN Explainer website, which is my favorite resource for learning about convolutional neural networks. And of course, we could spend 20 minutes clicking through everything here to find out what's going on with a convolutional neural network. Or we could start to code one up. So how about we do that, hey? If in doubt, code it out. So we're going to create a convolutional neural network. And what I'm going to do is I'm going to build this, or we're going to build this model together in this video. And then because it's going to use layers or PyTorch layers that we haven't looked at before, we're going to spend the next couple of videos stepping through those layers. So just bear with me as we code this entire model together. We'll go break it down in subsequent videos. So let's build our first convolutional neural network. That's a mouthful, by the way. I'm just going to probably stick to saying CNN. Fashion MNIST. We're up to model v2. We're going to subclass nn.module, as we always do when we're building a PyTorch model. And in here, we're going to say model architecture that replicates the tiny VGG. And you might be thinking, where did you get that from, Daniel? Model from CNN Explainer website. And so oftentimes when convolutional neural networks or new types of architecture come out, the authors of the research paper that present the model get to name the model. And so that way in the future, you can refer to different types of model architectures with just a simple name like tiny VGG, and people kind of know what's going on. So I believe somewhere on here it's called tiny VGG. Tiny VGG. We have nothing. Yeah, there we go. In tiny VGG. And do we have more than one tiny? Tiny, yeah, tiny VGG. And if we look up VGG, ConvNet, VGG16 was one of the original ones. VGG, Very Deep Convolutional Neural Networks, VGGNet. There's also ResNet, which is another convolutional neural network. You can also, I don't want to give you my location, Google. You can go popular CNN architectures. And this will give you a fair few options. LaNet is one of the first, AlexNet, ZFNet, whole bunch of different resources. And also, how could you find out more about a convolutional neural network? What is a convolutional neural network? You could go through that. But let's stop that for a moment. Let's code this one up together. So we're going to initialize our class here, def init. We're going to pass it in an input shape, just like we often do. We're going to put in a number of hidden units, which is an int. And we're going to put in an output shape, which is an int. Wonderful. So nothing too outlandish that we haven't seen before there. And we're going to go super.init to initialize our initializer, for lack of a better way of putting it. Now, we're going to create our neural network in a couple of blocks this time. And you might often hear when you learn more about convolutional neural networks, or I'll just tell you that things are often referred to as convolutional blocks. So if we go back to our keynote, this combination of layers might be referred to as a convolutional block. And a convolutional block, a deeper CNN, might be comprised of multiple convolutional blocks. So to add to the confusion, a block is comprised of multiple layers, and then an overall architecture is comprised of multiple blocks. And so the deeper and deeper your models get, the more blocks it might be comprised of, and the more layers those blocks may be comprised of within them. So it's kind of like Lego, which is very fun. So let's put together an NN sequential. Now, the first few layers here that we're going to create in conv block 1 are nn.conv2d. Oh, look at that. Us writing our first CNN layer. And we have to define something here which is in channels. So this channels refers to the number of channels in your visual data. And we're going to put in input shape. So we're defining the input shape. This is going to be the first layer in our model. The input shape is going to be what we define when we instantiate this class. And then the out channels. Oh, what's the out channels going to be? Well, it's going to be hidden units, just like we've done with our previous models. Now, the difference here is that in nn conv2d, we have a number of different hyperparameters that we can set. I'm going to set some pretty quickly here, but then we're going to step back through them, not only in this video, but in subsequent videos. We've got a fair bit going on here. We've got in channels, which is our input shape. We've got out channels, which are our hidden units. We've got a kernel size, which equals 3, or this could be a tuple as well, 3 by 3, but I just like to keep it as 3. We've got a stride and we've got padding. Now, because these are values we can set ourselves, what are they referred to as? Let's write this down. Values we can set ourselves in our neural networks, in our NNs, neural networks, are called hyperparameters. So these are the hyperparameters of NN-conv2D. And you might be thinking, what is 2D for? Well, because we're working with two-dimensional data, our images have height and width. There's also conv1D for one-dimensional data, 3D for three-dimensional data. We're going to stick with 2D for now. And so what do each of these hyperparameters do? Well, before we go through what each one of them do, we're going to do that when we step by step through this particular layer. What we've just done is we've replicated this particular layer of the CNN Explainer website. We've still got the ReLU, we've still got another conv and a ReLU and a max pool and a conv and a ReLU and a conv and a ReLU and a max pool. But this is the block I was talking about. This is one block here of this neural network, or at least that's how I've broken it down. And this is another block. You might notice that they're comprised of the same layers, just stacked on top of each other. And then we're going to have an output layer. And if you want to learn about where the hyperparameters came from, what we just coded, where could you learn about those? Well, one, you could go, of course, to the PyTorch documentation, PyTorch NN-conv2D. You can read about it there. There's the mathematical operation that we talked about or briefly stepped on before, or touched on, stepped on. Is that the right word? So create a conv layer. It's there. But also, this is why I showed you this beautiful website, so that you can read about these hyperparameters down here. Understanding hyperparameters. So your extra curriculum for this video is to go through this little graphic here and see if you can find out what padding means, what the kernel size means, and what the stride means. I'm not going to read through this for you. You can have a look at this interactive plot. We're going to keep coding, because that's what we're all about here. If in doubt, code it out. So we're going to now add a ReLU layer. And then after that, we're going to add another conv2D layer. And the in channels here is going to be the hidden units, because we're going to take the output size of this layer and use it as the input size to this layer. We're going to keep going here. Out channels equals hidden units again in this case. And then the kernel size is going to be 3 as well. Stride will be 1. Padding will be 1. Now, of course, we can change all of these values later on, but just bear with me while we set them how they are. We'll have another ReLU layer, and then we're going to finish off with the NN max pool 2D layer. Again, the 2D comes from the same reason we use conv2D. We're working with 2D data here. And we're going to set the kernel size here to be equal to 2. And of course, this can be a tuple as well, so it can be 2, 2. Now, where could you find out about NN max pool 2D? Well, we go NN max pool 2D. What does this do? Applies a 2D max pooling over an input signal composed of several input planes. So it's taking the max of an input. And we've got some parameters here, kernel size, the size of the window to take the max over. Now, where have we seen a window before? I'm just going to close these. If we come back up, where did we see a window? Let's dive into the max pool layer. See where my mouse is? Do you see that 2 by 2? Well, that's a window. Now look at the difference between the input and the output. What's happening? Well, we have a tile that's 2 by 2, a window of 4, and the max, we're taking the max of that tile. In this case, it's 0. Let's find the actual value. There we go. So if you look at those 4 numbers in the middle, inside the max brackets, we have 0.07, 0.09, 0.06, 0.05, and the max of all those is 0.09. And you'll notice that the input and the output shapes are different. The output is half the size of the input. So that's what max pooling does, is it tries to take the max value of whatever its input is and then outputs it on the right here. And so as our data This is a trend in all of deep learning, actually. As our image moves through, this is what you'll notice. Notice all the different shapes here. Even if you don't completely understand what's going on here, you'll notice that the two values here on the left start to get smaller and smaller as they go through the model. And what our model is trying to do here is take the input and learn a compressed representation through each of these layers. So it's going to smush and smush and smush, trying to find the most generalizable patterns to get to the ideal outputs. And that input is eventually going to be a feature vector to our final layer. So a lot going on there, but let's keep coding. What we've just completed is this first block. We've got a conv layer, a relu layer, a conv layer, a relu layer, and a max pool layer. Look at that. Conv layer, relu layer, conv layer, relu layer, max pool. Should we move on to the next block? We can do this one a bit faster now because we've already coded the first one. So I'm going to do nn.sequential as well. And then we're going to go nn.conv2d. We're going to set the in channels. What should the in channels be here? Well, we're going to set it to hidden units as well because our network is going to flow just straight through all of these layers. And the output size of this is going to be hidden units. And so we want the in channels to match up with the previous layer's out channels. So then we're going to go out channels equals hidden units as well. We're going to set the kernel size. Kernel size equals 3, stride equals 1, padding equals 1. Then what comes next? Well, because the two blocks are identical, the conv block 1 and conv 2, we can just go the exact same combination of layers. nn relu, nn conv 2d, in channels equals hidden units, out channels equals, you might already know this, hidden units. Then we have kernel size equals 3. Oh, 32, don't want it that big. Stride equals 1. Padding equals 1. What comes next? Well, we have another relu layer. Relu. And then what comes after that? We have another max pool. And then max pool 2D, kernel size equals 2. Beautiful. Now, what have we coded up so far? We've got this block, number 1. That's what this one on the inside here. And then we have conv2, relu2, conv2, relu2, max pool 2. So we've built these two blocks. Now what do we need to do? Well, we need an output layer. And so, what did we do before when we made model 1? We flattened the inputs of the final layer before we put them to the last linear layer. So flatten. So this is going to be the same kind of setup as our classifier layer. Now, I say that on purpose because that's what you'll generally hear the last output layer in a classification model called, is a classifier layer. So we're going to have, these two layers are going to be feature extractors. In other words, they're trying to learn the patterns that best represent our data. And then this final layer is going to take those features and classify them into our target classes, whatever our model thinks best suits those features, or whatever our model thinks those features that it learned represents in terms of our classes. So let's code it out. We'll go down here. Let's build our classifier layer. This is our biggest neural network yet. You should be very proud. We have nn.sequential again, and we're going to pass in nn.flatten because the output of these two blocks is going to be a multi-dimensional tensor, something similar to this size, 13, 13, 10. So we want to flatten the outputs into a single feature vector, and then we want to pass that feature vector to an nn.linear layer. And we're going to go in features equals hidden units times something times something. Now the reason I do this is because we're going to find something out later on, or times 0, just so it doesn't error. But sometimes calculating what your in features needs to be is quite tricky. And I'm going to show you a trick that I use later on to figure it out. And then we have out features, relates to our output shape, which will be the length of how many classes we have, right? One value for each class that we have. And so, with that being said, let's now that we've defined all of the components of our tiny VGG architecture, there is a lot going on, but this is the same methodology we've been using the whole time, defining some components, and then putting them together to compute in some way in a forward method. So forward self x. How are we going to do this? Well, we're going to set x is equal to self conv block 1 x. So x is going to go through conv block 1. It's going to go through the conv2d layer, relu layer, conv2d layer, relu layer, max pool layer, which will be the equivalent of an image going through this layer, this layer, this layer, this layer, this layer, and then ending up here. So we'll set it to that, and then we can print out x.shape to get its shape. We'll check this later on. Then we pass x through conv block 2, which is just going to go through all of the layers in this block, which is equivalent to the output of this layer going through all of these layers. And then because we've constructed a classifier layer, we're going to take the output of this block, which is going to be here, and we're going to pass it through our output layer, or what we've termed it, our classifier layer. I'll just print out x.shape here so we can track the shape as our model moves through the architecture. X equals self.classifier x. And then we're going to return x. Woohoo! Look at us go! We just built our first convolutional neural network by replicating what's on a CNN Explainer website. Now, that is actually very common practice in machine learning, is to find some sort of architecture that someone has found to work on some sort of problem and replicate it with code and see if it works on your own problem. You'll see this quite often. And so now let's instantiate a model. We'll go torch.manual seed. We're going to instantiate our first convolutional neural network. Model 2 equals fashion mnist. We will go model v2, and we are going to set the input shape. Now, what will the input shape be? Well, our conv2d layer up here, the input shape is the number of channels in our images. So do we have an image ready to go? Image shape. This is the number of color channels in our image. We have 1. If we had color images, we would set the input shape to 3. So the difference between our convolutional neural network, our CNN, TinyVGG, and the CNN Explainer, TinyVGG, is that they are using color images. So their input is 3 here. So 1 for each color channel, red, green, and blue. Whereas we have black and white images, so we have only 1 color channel. So we set the input shape to 1. And then we're going to go hidden units equals 10, which is exactly the same as what TinyVGG has used. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that sets the hidden units value of each of our layers. That's the power of creating an initializer with hidden units. And then finally, our output shape is going to be what? We've seen this before. This is going to be the length of our class names, 1 value for each class in our data set. And of course, we're going to send this model to the device. We're going to hit Shift and Enter. Oh no, what did we get wrong? Out channels, output shape. Where did I spell wrong? Out channels, out channels, out channels. I forgot an L. Of course, typo. Oh, kernel size, another typo. Did you notice that? Kernel size, kernel size, kernel size, kernel size. Where did we spell this wrong? Oh, here. Kernel size. Are there any other typos? Probably. Beautiful. There we go. Okay, what have we got? Initializing 0 op tensors is a non-op. Oh, so we've got an issue here, an error here, because I've got this. But this is just to, there's a trick to calculating this. We're going to cover this in another video, but pat yourself on the back. We've written a fair bit of code here. This is a convolutional neural network that replicates the TinyVGG architecture on the CNN Explainer website. Now, don't forget, your extra curriculum is to go through this website for at least 20 minutes and read about what's happening in our models. We're focused on code here, but this is particularly where you want to pay attention to. If you read through this, understanding hyperparameters, and play around with this, the next couple of videos will make a lot more sense. So read about padding, read about kernel size, and read about stride. I'll see you in the next video. We're going to go through our network step by step.